name is Casey Moglevsky, and I'm with PEACE Tutoring. And today I'll be talking with all of you about carbonyl chemistry. So this is a topic that's found in Chem 3B at Berkeley and also Chem 12B at Berkeley. But it can also be found kind of sprinkled into some of the biochemistry classes like MCB 102 and Chem 135, MCB 100B. Because many biological reactions take advantage of this chemistry to perform very important transformations that occur. So really quick, before we dive into the meat of everything, what do I mean by carbonyls? Well, in the specific sense of carbonyl, we mean something that's like this, a carbon that's double bonded to an oxygen. And these R groups, as they're found in organic chemistry, can be anything. They're sometimes other carbons, it can be oxygen, many other things. The important part is that you have this carbon-oxygen double bond. But there are also a few other types of atoms actually, that can take the place of this oxygen and offer a similar level of reactivity and participate in similar reactions. So these can be NH, so a nitrogen with a hydrogen attached to it, which is isoelectronic, or at least on the nitrogen is isoelectronic to oxygen. Or it could be a sulfur atom, which is one row down from oxygen. And these types of compounds react very similarly and participate in similar reactions. Okay, so why does it happen like this? Why are these carbonyls, or these carbonyl-like compounds, have this type of reactivity? Well, it has everything to do with the difference in electronegativity between carbon and these heteroatoms, as they're called in organic chemistry. And as you may know, that carbon is relatively in the middle of the electronegativity scale, where it's around 2.2-ish. Hydrogen is around 2 point something-ish, I'll say 2.6-ish, I think. And oxygen is around 3.4. Nitrogen is around 3. And sulfur is also around 3-ish. So what this does to these sorts of molecules is that you have a really big electronegativity difference between two atoms that are right next to each other. So you have, let's say in this case, oxygen and carbon. And we're gonna actually do a real life example that many of you might be familiar with, which is acetone, found in many nail polish removers, for example. So acetone, this carbon here is going to have a delta positive charge, partial positive, and this oxygen is going to have a partial negative charge, kind of similar to how water is polarized. But in this case, this partial positive charge on the oxygen right here, on the carbon right here, makes this very electrophilic. So what do we mean by that? Electrophilic carbon means that it's electron poor, its electrons are being sucked away by this oxygen, and it wants to have some electrons donated to it from another source. And in organic chemistry, many of you might be familiar with that thing, or the just general class of that thing that is able to donate these electrons that this carbon so desires. And those are called nucleophiles. And these can be anything from thiols to thiolates, for example, amines, amides. Amides in the sense of the deprotonated amines. Grignard reagents. Alkyl lithium reagents. And many, many more. So these, let's take the case of the amine, for example. So the amine has a lot of electron density in this lone pair, or on this nitrogen, because it's also electronegative and will suck the electrons away from these R groups, which are usually carbons, or also hydrogen sometimes. And this lone pair of electrons can, and we're going to use the arrow notation from OChem, go and attack this electrophilic center, the carbon. And this happens because this nitrogen is very electron rich, and it's very willing to give its electrons to this very, very electron poor carbon and participate in a reaction. So the transformation that will ensue looks kind of like this. And let's say that this is this amine right here is ammonia. So it'll be NH3. And let's say that this reaction participates in water, or there's some water present. So what will happen is that this lone pair is going to attack this carbon right here. And this carbon can't have 5 bonds. So the electrons from this double bond, one of the pairs of electrons that are participating in this bond, are going to go up to this oxygen. And I usually like to always draw in my lone pairs on stuff while I'm doing these arrow pushings, because it really helps. And actually, I should redraw this so that it doesn't look like the arrow is going to another pair of electrons. So the electrons are going to transfer kind of like this. And as an intermediate, you're going to get this species. Oh, just acetone. And you're going to have 3 lone pairs on this. Okay, so what happens now? Well, a variety of things can happen, but what usually happens in this case is that of what's called a proton transfer. And basically what a proton transfer is that one of the hydrogens from here or more are going to get transferred from one of these heteroatoms to the other. And this is facilitated once again by this protic solvent. It can be water, there's sometimes acid or base usually in the solvents. And so a proton transfer will occur. And we can go into the direct mechanism, but it's basically just a couple of acid-base reactions. And most OChem teachers at Berkeley will let you just write proton transfer. Now, of course, you can. One could argue about whether if it's a good practice to try to draw the exact proton transfers at least your first few times, but it's up to you. So then what this will form is this species. And then we have an elimination reaction afterwards. This pops off. And this is what's called a tetrahedral intermediate. And this final species, it's called an iminium ion. But this can participate further because it's also a similarly electrophilic carbon center right here. Now, usually something that I actually forgot to mention is that sometimes, and actually in the case of this reaction, sometimes the nucleophile isn't a good enough nucleophile, and sometimes the carbonyl isn't electrophilic enough. And so sometimes, and even, this reaction might not occur at an appreciable rate unless it's acid or base catalyzed. Now, this reaction can certainly occur, but it's often helped along by having extra acid or extra base in the solution. So let's go through two examples and say, for example, let's go through the reaction to form a hemiacetal or an acetal. Okay, so let's do the hemiacetal example first. So let's start from acetone again. And we want to see what happens when we do this reaction with methanol, for example. Not great nucleophile. Certainly is nucleophilic-ish, but it won't do this reaction to an appreciable level, at appreciable speed, unless we help it along with either acid or base. So it turns out that hemiacetals, the reaction to form this can be both acid and base catalyzed. So let's do the base example first. So we're going to have in this reaction, say methanol, MEOH. And we're going to have some sort of base. It can be sodium hydroxide. It's in catalytic amounts. But if you want to be, extra careful, if you're a really good organic chemist, you can just say sodium methoxide, NaOMe. Or as I like to call it, Naomi. Okay, and I actually won't draw the final product right now, so let's just go through the mechanism for how this will form, how this will proceed. So out here we have a methanol. Actually, let's draw this as the methoxide since we already have that. So this methoxide is a much better nucleophile than just methanol due to the extra negative charge around the oxygen. So this can do is this similarly can attack this carbon right here, and it will form a tetrahedral intermediate again. So now we have this as our product, but this negatively charged deprotonated oxygen right here is very, very unhappy. So what it's going to do is it's going to just take a proton from the nearest thing that's a proton donor. And in this case, that'll just be another methanol. And as a final product, we have the hemiacetal. Hemiacetal. Hemi meaning half, and this is because it's half of a full acetal, which we'll talk about in a second. So what's cool and what I mean by base catalysis is that after you do this reaction once, you have more of this, the methoxide, to go and react again with the acetone. Another interesting thing is that base catalysis will only afford you the hemiacetal. You can never make the full acetal from base catalysis. And why might that be? Well, because you don't ever have a good leaving group by which you can do an SN2 reaction, for example, or an SN1 reaction, because this OH here is just not a good leaving group. Neither is this methyl ether right here. But in contrast, let's go talk about the acid catalyzed version of this reaction. So let's say, once again, that we have acetone. And we're going to try to do the reaction where we say we want methanol. And let's say that we have catalytic acid. It doesn't really matter what kind of acid it is. I mean, it does a little bit, but for this example, it doesn't really matter. So let's just say H plus catalytic, which means it's like percentage on a mole percentage value. It's like 1% or something. So we have this H plus, and what is this H plus going to do? Well, it can protonate a variety of things, but one of the things that it can protonate is the oxygen of the carbonyl. And what you're going to form is this positively charged protonated carbonyl. Now, many of you might be wondering, okay, so how does this help? Why do we want to do this? Well, I know we're drawing it with a positive charge on the oxygen, but because the oxygen is bonded to the carbon, this positive charge will also exist somewhat on the carbon. And moreover, a larger percentage of this positive charge is actually going to exist on the carbon than the oxygen because oxygen is so electronegative. Basically, by adding a proton onto this oxygen and making it positively charged, we make it even more willing to suck electron density from this carbon right here. So this is an even bigger partial positive right here. And an even bigger, well, it's not even partial negative anymore. It's just slightly less partial positive. So let's do a little one, like little partial positive right here. Okay, so what this does, in essence, is just make this carbon right here much, 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 much more electrophilic by virtue of the oxygen pulling more electron density from it. Okay, let's see what this gets us. So now we have a methanol nucleophile, and we said that alcohols aren't really great nucleophiles, but because this is so electrophilic, this is very electrophilic. It really, really wants electrons from somewhere. Doesn't really care. It'll react with the methanol. So we'll take a lone pair from this, attack this carbon, and push electron density up to this oxygen. Okay, where will this get us? So this is going to get us to this species. Oops. Okay, cool. Now, what we can do is we can do a proton transfer. And something that I actually forgot by mistake to mention earlier is that all proton transfer reactions are equilibrium. And I'm going to abbreviate that as PT. So if we actually go back up here, this should be an equilibrium reaction. Okay, back to this problem. We're going to get this species. Now, why did we want to do this? Well, we can say that this over here is a good leaving group, but if we have that be the leaving group, we get the same thing as a final product. So that can happen in equilibrium, and it will, but it doesn't really get us anywhere, so we're just going to pretend that it doesn't happen. Okay, so what can we do with this? Well, thinking back to some Chem 12A stuff, some Chem 3A stuff, this is also a really good leaving group. And we also have a decent-ish nucleophile. Okay, so what we can do is we can eliminate this and get electron density to come down from this oxygen and get this species right here. Now this is going to be not an equilibrium reaction because there just isn't a lot of the water that's being produced from here. Perhaps later the equilibrium errors are going to look like this, but initially right now it's going to look like this. Very, very small equilibrium error. Pretty much not an equilibrium reaction. So I guess now you can see why if we just eliminated this thing, we would get back to here. And certainly that can happen. And so this is actually also an equilibrium reaction. Okay, so then what do we do with this? Well, this is also very similarly very electrophilic. Maybe draw a better circle. Okay, and then we have more methanol. We can do a similar reaction. What do we get from this? We get let's draw that better. MEH plus OMe. We get a protonated acetal. And this is one step away from turning into your final acetal. And actually, the proton here, it goes into solution. It can protonate methanol, but it also could protonate another one of those acetones. So this is why we think of this as acid catalyzed, because you only need to add a small amount of acid for this to actually occur. Okay. And I hope now you can appreciate potentially why this over here, this base catalyzed mechanism, could only give you the hemiacetal, because this is not a good leaving group. No matter how good you make this methoxy nucleophile, I mean, it's not great of a nucleophile even in that case, but no matter how good you make it, this still is not a good enough leaving group. You can't do an elimination because you're kicking off hydroxide, not a very stable thing to kick off. Whereas here, you're kicking off water, which is a lot more stable. It's pretty happy to just be water leaving. Water is a very good leaving group. Okay, so those are just acetals and hemiacetals. And I guess really quickly before I go into the next section, let's talk about some different types of things that also are carbonyls, kind of like the iminium ion that we talked about earlier. But in this case, let's just dive in. Let's just dive in. So, table of carbonyls. So we have this is an aldehyde. And these R groups are R equals carbon something. Okay, so this is a ketone. Many of you might be familiar with this. This next one, which is carboxylic acid. Then we have esters, which is basically just you replace the hydrogen, the proton, with another R group that's carbon something something something. Can be anything actually. Then next we have acid anhydrides. And finally, we have, of the common carbonyl groups, we have acid halides. And I'm going to denote this as an X. Oh, actually, did forget to mention one. Amides. Amides in the carbonyl sense of the word. And amides can have NH2 there or NLR2. It can be in amino acid polypeptide backbones. Anything can be in this R group that's not like another nitrogen or something. Okay, so we have all of these wonderful things right here. How do they compare with each other in terms of reactivity? Well, as it turns out, if we were to put them on a scale, and I'm going to make two separate scales, and you'll see why in a second, separate scales of the reactivity of these things. Chart. Way at the bottom, let's say hi. Blue. Way at the bottom, you have your amide. Then above your, actually even below the amide, let's do even lower than that. There is something that's lower than this. You have your deprotonated carboxylic acid, and that's very important. Your amide, and then you have your ester / protonated carboxylic acid. Over here, you have your aldehyde. Just be up a little bit. And your ketone. So aldehydes are actually more reactive than ketones. We'll discuss why in a second. And then you have your acid anhydride. And finally, you have your acid chloride. Or acid halide. The halide can be iodide, chloride, bromide. It's usually chloride. So why does this occur? Many of you might be asking. It's due entirely to resonance. So first talking about all of these, let's talk about the ones at the bottom. So you can draw two resonance structures for this deprotonated carboxylic acid, for example, and these are actually equal contributors, equal resonance contributors. And we'll see why in a second. Why they're equal resonance contributors is that one of these structures is not actually more stable than the other ones. And this is why these deprotonated, this is why acids, carboxylic acids, have the structures because they can distribute the negative charge that results over to electronegative atoms, such as oxygen. Okay, the next thing that's up is an amide. Now, this one might be a little bit more obscure as to why this occurs, but you can actually similarly draw resonance structures with amides. There's only two pairs of electrons there. And this nitrogen actually has a lone pair here. And you'll get this structure. Now, I hope that many of you can appreciate. Oops, let me draw this a little bit better. Many of you can appreciate why this is this is not an equal resonance contribution. Because this structure is not as good of a resonance structure. There's separated charges. It's not particularly stable. But why this is slightly more stable, or this particular structure here is more stable than its respective counterpart in, say, an ester or carboxylic acid that's protonated. We'll see why in a second, but those, for example, can participate in similar resonance, and I'll draw that out, and then we can compare exactly how this looks like. And I'll just do this as an ester. Let's do this, 2 lone pairs. Now, I guess, let me ask, comparing these two, which might be a more stable resonance structure for these sorts of molecules? So it'd actually be the nitrogen containing one, because nitrogen is less electronegative than oxygen. And let's say it's less unhappy. It's less angry about having a positive charge, a positive formal charge on itself. So this contributes more. This resonance structure contributes more. And if we were to draw these arrows to scale, let's draw this in black. The one at the very top is equal. This one has a big arrow, big back arrow, and a smaller front arrow. But this one has an even bigger back arrow and a smaller front arrow. So much less of this carboxylic acid or ester exists in this other form. So quickly looking at these three, what you might see is that if you have this sort of structure here, the electron density on this carbon is actually getting pulled 2 ways. It's getting pulled this way and it's getting pulled this way. But that means overall, less of it is getting pulled away from the carbon, because it's there's like this tug of war and these oxygens are fighting with each other for this electron density. And you actually have less electrophilic character here. Even in these resonance structures, you can see that you have this electron poor carbon right here, and it's next to a very electron rich oxygen, such that it can just donate its electrons and form this other resonance structure, and it just flip flops. So this carbon, this electrophilic center, is overall much, much, much less electrophilic than, for example, here, this aldehyde, for example. One could say that this oxygen is electron donating. It's donating some of its electrons into this resonance system, which helps stabilize, or no, let's not say stabilize, it helps make this carbon less reactive. Similarly, the amide can do a similar thing, and the ether or the protonated carboxylic acid can do a similar thing, but they just don't have as stable resonance structures, the alternative resonance structures. So they don't have as much contribution, and they don't have as much electron donation character into this resonance system. So these are comparatively more electrophilic, so more electrophilic than this one. And this one is also more electrophilic. Than this one. Okay, so let's really quickly talk about the aldehyde and the ketone, for example. Why those might be differently reactive. And I put them in a little bit of a separate class because they participate in slightly different reactions than the ones on the right of this chart, which we'll get into in the next video. So aldehydes and ketones. So aldehydes R equals CH, some sort of carbon group, or it can just be another hydrogen in the case of formaldehyde. And ketones look like this. They have 2 carbon R groups on them. It actually turns out that carbon, say methyl groups or ethyl groups or benzyl groups or what have you, they actually are slightly electron donating. And what they can do is they can give some of their electrons to this carbonyl carbon right here, as I like to call it. So aldehydes are actually more reactive, more electrophilic. As compared to ketones, because they only have 0 or 0 in the case of formaldehyde, but 1 in the case of, say, something like acetaldehyde, R group donating electrons into this carbon, this electrophilic carbon right here. Okay, so as we talked about earlier, hydrogen is slightly more electronegative than carbon. So what does that mean? It means very, very slightly, this hydrogen is pulling some electron density from this carbon, just very, very, very slightly, since hydrogen is about 2.6 and carbon is about 2.2. And if you have something that's 2 of the same atom next to each other, you're not really going to have any electron density being pushed or pulled to one area. So what does that mean is that methyl groups or ethyl groups or benzyl groups, they're electron donating, not necessarily because they're really electron donating to the carbon, it's just that they're not sucking electron density away from it. Or you can say in terms of van der Waals, permutations of electrons shuffling around, that since there's no difference in electronegativity between 2 carbons next to each other, that second carbon is very willing to just share some of its electrons. So they're similar electronegativity. So what this means is that this is less electrophilic because there's more electron density right here, because there's more methyl groups, ethyl groups, benzyl groups, what have you, attached directly to it. Versus this aldehyde right here has 1 hydrogen group that's not really donating its electron density. It's not sharing as much compared to another carbon. As you can imagine, that makes the aldehydes more reactive, more electrophilic. To give a particular example of this, in terms of making the hydrate, for example, of a particular aldehyde or ketone, if we were to draw a few of the examples, so let's say formaldehyde, acetaldehyde, and acetone, if we wanted to do the respective reactions to where they form the hydrate, which is the nucleophilic attack of water, with formaldehyde, this happens much, much, much more frequently than it does with acetone, for example. And so if these are equilibrium arrows, because as always, these reactions are in equilibrium, this will look something like this. So as you can see, this is much more willing to, say, the carbonyl of formaldehyde is much more willing to participate in this reaction than the carbonyl of an acetone, for example. And experimentally, you find that a higher percentage comparatively of formaldehyde water mixtures of similar composition or similar mole fraction compositions to acetone water mixtures are actually have the formaldehyde in the hydrated form, this form right here, versus the hydrated form of the acetone comparatively. And that's all due to just the differences in the electrophilic character of this carbon right here, the carbonyl carbon. And I'm sure this example has been talked about in your Chem 3B, Chem 12B classes. Okay, so the last two, really quick, are the acid anhydride and the acid halide. And it turns out that acid anhydrides are slightly less reactive than acid halides, but both of them are really reactive precisely because there really isn't a good resonance structure. And I'll try to draw that for the acid anhydride and the acid halide. So, if we're trying to do resonance structure, well, so you can see what might happen is that there's two carbonyls that want to pull the electron density from this carbon. And what happens is that this oxygen is trying to share. And it just doesn't really form any stable, resonance structures. You can try to do it like this. But this is really not stable because it's trying to do it with the other one, and it's not exactly the happiest molecule right there. And in the case of the acid halide, let's do chlorine, for example, acid chloride. If we try to do this resonance structure, well, chlorine is an incredibly electronegative atom. Something similar to carbon, something similar to oxygen, it's around 3.4. Oops. So this is a very, very unhappy structure right here, very unstable resonance contributor because you have a formable positive charge on the chlorine. And so similarly, this resonance structure basically is non-existent, and so you have much more electron density being pulled from this oxygen. Moreover, sorry, this carbon. Moreover, you have two very electronegative atoms next to a carbon, and it really makes this this carbon right here very, very electrophilic. Okay, so lastly, this difference in reactivity, at least for these, not talking about the acetone and the formaldehyde, the second difference comes in terms of the ability for the leaving group to be stable. So really quickly, let's talk about leaving group. And the leaving group for these, and this is why this is different than the aldehyde and ketones, is that you have no leaving group. LG for leaving group. But the leaving group, stability. The leaving group is going to be a halide, like a deprotonated conjugate base of a hydrochloric acid or hydrobromic acid, for example. And as we know, those are very strong acids. So this is very stable, very stable. The pKa of conjugate acid is less than 0. Very, very strong acids. Similarly, this is a deprotonated carboxylic acid is your leaving group for this one. So stable. This is around 3 to 4-ish. Okay, let's go down to the ester and the alcohol. So assuming that you wouldn't first deprotonate the alcohol, or the OH here, the carboxylic acid, I mean, the leaving group is going to be OR minus. And all of these deprotonated alcohols, or deprotonated water, for example, would have a pKa of the conjugate acid being the methanol or water. It's around 14 to 15. Okay, next we have the amide. So this would leave, and it would leave a amide leaving group. Sometimes, this is why they kind of share the name with the amides we talked about before. Very not stable. pK of this is like 25 of the conjugate acid of this amide leaving group right here. And finally, well, what would the leaving group of this deprotonated carboxylic acid be? It would be O-2, doubly deprotonated oxygen. Basically, this never happens. That is an incredibly, incredibly unstable thing to have, is just naked oxygen that's doubly negatively charged. Like oxygen might be pretty electronegative, but nothing is that electronegative to make that a stable state. And I don't even know. I don't think anyone really knows what the pKa of this would be. It's probably measured by someone somewhere, but let's just say greater than like 50, which is 50, for example, is the pKa of a carbon-hydrogen bond, for example. pKa of like methane or something. So that's like the second reason that this sort of hierarchy of reactivity occurs, is additionally because of the ability for this leaving group to leave. And this only applies to these ones right here. Let's use rainbow. These here, the acid derivatives. So lastly, before I go in the last 5 minutes, and we'll talk about these sorts of reactions in the next video, is what can these acid derivatives or just this leaving group, what can the addition of this leaving group do? Well, what you can do is you can, similarly to SN2 or SN1, you can substitute it for something else, something that's nucleophilic. And common mistakes with these reactions in drawing the arrows is to draw them or think of them kind of like an SN1 or SN2 reaction. And they don't really happen that way. And if we look back, actually, to tie it back into something we talked about earlier, these reactions are actually kind of similar to the second part of this this acetal formation. And if you could somewhat imagine it, this is as if you had a protonated, you can think of this kind of like the product as if you had a protonated ether, which would leave it to be a very, very good leaving group, for example, or protonated carboxylic acid, like a doubly protonated carboxylic acid, which that probably would never really happen, but you can kind of think of it like that to just tie it back into something we talked about earlier. Okay, so really quick, what's the general structure of these substitution reactions? Let's do, partially because it's really easy to draw, let's do an acyl chloride reacting with, what's the nucleophile of the day? Let's make an amide. So let's say we're reacting this with glycine, for example, to tie it into some biochemistry examples. Glycine, let's be even fancier. Let's say phenylalanine. So phenylalanine is going to look like this. 2N. Oops, I drew that wrong. And let's say that this is a protected phenylalanine. And pH for phenyl, so this is phenylalanine. Okay, so what's this going to do? Well, I don't really want to redraw this. I'll just draw it from here. First step at least. So this is going to do that, attack the carbonyl from the amine, and you're going to form negative charge on the oxygen in this chemical tetrahedral intermediate. So chloride. And then NH, and then the rest of the phenylalanine group. Okay, so then now we have this tetrahedral intermediate. And we can pull the electron density back down and kick off this chlorine as chloride as a leaving group, a good, very, very good leaving group. And we're also going to do some proton transfers after that, get the charge back off of this amide nitrogen right here. And so what have we formed? Well, we formed an amide, which is cool. But where are these important? Well, these are important for proteins, polypeptides, being the backbones of proteins. And in biology, this is actually called a peptide bond, biochemistry, and such. Polypeptide linkage. And being so important for us, as you would imagine, nature has found a way to make this reaction happen in real life, at neutral pH and in water. But overall, as you would imagine, this type of reactivity is very, very important. And it's important to life, and it's important to chemistry. Here's just a small example before we dive into the differences. Different reactions you can do with these acid derivatives in the next video. But yeah, so overall, to summarize what we covered today. So we talked about carbonyls, why they react like this, have the electrophilic nature of the carbon, the carbonyl carbon. Talked about some common reactions that occur. Talking about some acid derivatives, how their resonance stability helps stabilize them or destabilize them to give them different reactivities. The identities of the leaving groups that occur and how that also plays into these different reactivities. How electron donating character and electron withdrawing character plays into these reactivities, the differences, especially in the aldehyde versus ketone case. And finally, how we did a small example of a substitution reaction with carboxylic acid derivatives. So I'd like to thank you for watching and getting this far. I know it's been a really long video, but I hope to see you in the next one.